Hello everyone, welcome to my channel Regular Learning Academy. I am Dr. Krishna Sarker, Department of Electrical Engineering. Here in this session, I will be going to discuss about stability for describing function analysis. That means stability or stable and unstable limit cycle. Department of Electrical Engineering, Nonlinear Control Systems. This is lecture number 4. So our topic's name, stability for describing function analysis. Overview, describing function analysis of nonlinear control systems, closed loop frequency response, stable and unstable systems, stability of sustained oscillations or limit cycles. Limit cycle criterion, stable limit cycle, unstable limit cycle, accuracy of the describing function, advantage and disadvantage of describing function, conclusion and future direction of describing function. So, describing function analysis of nonlinear control systems. This is the basic block diagram for describing function analysis. And this section, this is the reference input, and input to the nonlinear element always sinusoidal. That means this signal always sinusoidal. And this is the comparator, and this is the nonlinear elements like saturation, dead zone, hysteresis, backlash, on-off relay, any type of nonlinear elements. And this is the nonlinear output, and this is the linear element. This is actually minimum phase filter or low pass filter, and this filter always stable because all the poles and zeros left hand side of the S plane, and this is the output of the systems. The output of the nonlinear element, this is the output of the nonlinear element. Output of the nonlinear element is periodic and of the same fundamental frequency as that of the input signal. The output of the nonlinear element is may be sinusoidal or may not be sinusoidal. Generally, may not be sinusoidal. Nonlinear system may have subharmonic also. Nonlinear system may have subharmonic, and this is the feedback path. Feedback path may be positive, may be negative. In this section, this is the negative feedback. Many control systems containing nonlinear elements may be represented by the block diagram shown in figure 1. This is the control system block diagram. If the higher order harmonics generated by the nonlinear elements are sufficiently attenuated by the linear elements so that only the fundamental harmonic component of the output of the nonlinear element is significant. That means in this section, higher order harmonics are generated by the nonlinear element, and by filter sufficiently attenuated the higher order harmonics. Only the fundamental harmonic component of the output of the nonlinear element is significant in output side. Then the stability of the system can be predicted by the describing function analysis. Describing function analysis, this is also block diagram. This nonlinear element gain equals to n. This is the nonlinear describing function n, and this is the linear gain equals to G of S, and reference input R of S, and the output, overall output C of S, and the unity feedback, and also this feedback negative. So nonlinear control system block diagram. This is the general block diagram. We shall first discuss how the describing function of nonlinear elements can be used for stability analysis of nonlinear control systems. We shall show that if the sustained oscillation exists in the system output, then the amplitude and frequency of the oscillation may be determined from the graphical study in the frequency domain. Describing function analysis continue. And this is also block diagram for general block diagram. So consider the system shown in figure 3. Consider the system shown in figure 3. The block diagram describing function n denotes the describing function of the nonlinear elements. So n denotes the describing function of the nonlinear elements. So this is the n denotes the describing function of the nonlinear element. If the higher order harmonics or higher harmonics are sufficiently attenuated, the describing function n can be treated as a real variable or complex variable gain. Then the closed loop response becomes Cs by Rs equals to n into Gs. This is the n and this is the Gs. So multiply n into Gs divided by 1 plus n into Gs, where 1 plus n into Gs equals to 0 is called characteristics equation. Is called characteristics equation, and this is the overall transfer function Cs by Rs for nonlinear control systems. Then the closed loop frequency response becomes Cj omega by R of j omega equals to n of Gj omega equals to n of Gj omega divided by 1 plus n of Gj omega, because input always sinusoidal. So put S is equal to j omega. Then we get C of j omega by R of j omega. This is the equation number 1. The characteristics equation is 1 plus n of Gj omega equals to 0. This is the characteristics equation for nonlinear control systems. And then we can write G of j omega. This is the G of j omega equals to minus 1 by n. So left hand side linear part and right hand side nonlinear part, and this is the reciprocal. So G of j omega equals to minus 1 by n. This is the condition for stability. If equation 3, this is the equation number 3, is satisfied, then the system output will be exhibited a limit cycle. This situation corresponds to a case where the G of j omega locus passes through the critical point. Critical point means minus 1 plus j0 point. In the conventional frequency response analysis of a linear control system, the critical point is the minus 1 plus j0 point. This is the critical point. So equation 3 is the very important for stability analysis. In the describing function analysis, the conventional frequency response analysis is modified so that the entire minus 1 by n locus becomes a locus of critical points. Thus, the relative location of the minus 1 by n locus and Gj omega locus will provide the stability information. So minus 1 by n locus for nonlinear system and Gj omega locus gives the stability information. If G of j omega equals to minus 1 by n, here shows that the intersection of the plot Gj omega with the plot of minus 1 by n as omega varies determines the amplitude and frequency of the limit cycle. G of j omega as omega varies and of minus 1 by n as the amplitude varies. Consider the system is stable in open loop for a frequency independent describing function, that is n of x omega equals to n of x. This is the frequency independent describing function. The closed loop stability can be determined using the following criterion. What is the criterion? G of j omega, that means linear part or minimum phase part. G of j omega locus does not encircle minus 1 by n, then the system is stable. This is the condition number 1 for stable. G of j omega locus does not encircle minus 1 by n. And second condition, G of j omega locus encircles minus 1 by n, and then the system is unstable. For what condition system will be unstable? When G of j omega locus encircle minus 1 by G of j omega locus does not encircle, then this is the G of j omega locus encircle minus 1 by n locus, then system is unstable. This is the condition number 2. And G of j omega intersects minus 1 by n locus, and then there is a possibility of existence of the limit cycle. So G omega locus intersects minus 1 by n locus, then possibility of the limit cycles, existence of the limit cycle. So case number 1. What is the case? Stable systems. This is the circuit diagram, or this is the output diagram. Nonlinear control systems and the stable systems diagram. And this is the z omega locus, and this is minus 1 by n locus. For nonlinear section, this is minus 1 by n locus. This is minus, not 1 by n. This is minus 1 by n locus. And this is z omega locus. And this section imaginary, and this is the real part. This is minus 1 plus j0 point, critical point. This point minus 1 plus j0 point. So outside minus 1 plus j0 does not intersect. That's why this is stable. So what is the condition? Case number 1. To determine the stability of the system, we plot the minus 1 by n locus. This is the minus 1 by n locus. This is minus 1 by n locus. And the z omega locus, this is z omega locus. Z omega locus. In the present analysis, we assume that the linear part of the system is of minimum phase, or that all poles and zeros of GS lies in the left half of the S plane, because this is minimum phase. That's why all the poles and zeros left hand side of the S plane, including the j omega axis. The criterion of stability is that. What is the criterion? If minus 1 by n locus is not enclosed by the z omega locus, then the system is stable. This is the stable condition, because minus 1 by n locus is not enclosed by the z omega locus, or there is no limit cycle at steady state, and there is no limit cycle. So this is the stable condition. And case number 2, unstable system. This is the unstable configuration. This is z omega locus, and this is minus 1 by n locus. This is not 1 by n. This is minus 1 by n locus. This is also minus 1 by n locus, and this is z omega locus. Nonlinear control systems, and the system is unstable. For what condition this will be unstable? This is case number 2. On the other hand, to determine the stability of the system, we plot the minus 1 by n locus and z omega locus. This is minus 1 by n locus. This is also minus 1 by n locus. This is z omega locus. This is also z omega locus. And minus 1 plus j0 point outside. Minus 1 plus j0 point. This is the minus 1 plus j0 point. In the present analysis, we assume that the linear part of the system is of minimum phase, or that all poles and zeros of CS lie in the left half of the S planes, including the j omega axis. The criterion for stability is that. What condition this will be? Unstable. If the minus 1 by n locus, this is the minus 1 by n locus, is enclosed by the z omega locus, then the system is unstable. This is enclosed by the z omega locus. So minus 1 by n locus, minus 1 by n locus enclosed by the z omega locus. That's why this is unstable. And the system output when subjected to any disturbance will increases until breakdown occurs or increase to some limiting value determining by the mechanical stop or other safety device. And sustained oscillation, this is also very important. Case number 3, sustained oscillation. For what condition this will be sustained? This is the configuration, and this the polar plot or z omega plot, and this is -1 by n locus. This is the -1 by n locus, and this is the intersection point 1, and this is intersection point 2. So limit cycle exists. Nonlinear control system with stable and unstable limit cycle, and one limit cycle unstable, another limit cycle stable. For case number 3, to determine the stability of the system, we plot the -1 by n locus. This is the -1 by n locus, and the z omega locus. This is the z omega locus. In the present analysis, we assume that the linear part of the system is minimum phase. That means all the poles and zeros left hand side of the S-plane, including the j omega axis. The criterion for the stability is, for what condition this will be sustained oscillation. If the -1 by n locus, this is the -1 by n locus, this is -1 by n locus, is intersects by the z omega locus. This is the z omega locus, and this is the intersection point, this is the intersection point, then the system output may exhibit a sustained oscillation or limit cycle. Here 2 points. This is one limit cycle, this is another limit cycle. Such a sustained oscillation is not sinusoidal, but it may be approximated by a sinusoidal one. The sustained oscillation is characterized by the value of x and of -1 by n locus and the value of omega on the z omega locus at the intersection. In general, a control system should not exhibit a limit cycle behavior, although a limit cycle or small amplitude of a small amplitude may be acceptable in certain application. This is the very important condition. Although a limit cycle of small amplitude may be acceptable in certain applications. Stability of sustained oscillation or limit cycle. So this is the z omega locus, and this is the -1 by n locus. This is the -1 by n locus, and this is one intersection point. This is unstable limit cycle. This is stable limit cycle. Stability analysis of limit cycle operation of nonlinear control system with stable and unstable. The stability of the limit cycle can be predicted as follows. Consider the control system shown in figure 7. Assume that point A, this is the point A, on the -1 by n locus. This is the -1 by n locus, and A on the -1 by n locus corresponds to a small value of x. X is the sinusoidal magnitude x, where x is the amplitude of the sinusoidal input signal to the nonlinear element. The point B on the -1 by n locus, another point B on the -1 by n locus corresponds to a large value of x. That means in this position, magnitude of x is small, and B position, magnitude of x value is large. So that's why this is x tends to 0. This position x tends to 0, and x increases. This is a small value, also increases, and finally x tends to infinity. The value of x on the -1 by n locus increases in the direction of the point A to point B. So -1 by n locus, value of x on the -1 by n locus. This is the -1 by n locus, value of x increases in the direction from the point A to point B. This is the direction. X increases 0 to x tends to 0 to x tends to infinity. Limit cycle criterion. What is limit cycle? Its interaction point of the curve gj omega and the curve -1 by n corresponds to a limit cycle. If points near the intersection and along the increasing point A said to be curve -1 by n are not encircled by the curve g of j omega, then the corresponding limit cycle is stable. Otherwise, the limit cycle is unstable. So, what is unstable limit cycle and what is stable limit cycle? First, what is unstable limit cycle? This is the configuration. So, this is z omega locus and this is -1 by n locus. This is the intersection point A, another intersection point B, and this side x tends to 0. This is the x tends to infinity. Stability analysis for analysis of limit cycle, operation of nonlinear control system with stable and unstable. Let the system is operating at point A. Let the system is operating at point A. This is the point A, which is a limit cycle. But this limit cycle stable or unstable? This is the important question. So next point. At this point, the oscillation has amplitude. At point A, oscillation of amplitude equals to x of A. This is the magnitude. And frequency omega A. That means at point A, magnitude equals to x of A, xa, and frequency equals to omega A, determined from the -1 by n locus and the z omega locus respectively. Then, if a slight disturbance causes the system operating point to move from point A to point C on the -1 by n locus. Suppose point A and slight disturbance, the point moves point A to point C. Then the operating point C corresponds to the critical point or to the -1 by -1 plus j0 point in the complex plane for linear control systems. Then the z omega locus in this case enclose the critical point, point C in the Nyquist sense, since this is similar to the cases where the open loop locus of a linear system enclose the -1 plus j0 point. So when some disturbance and point move point A to C, this is the inside -1 plus j0 point, and at that condition system unstable. So the amplitude of the sinusoidal input to the nonlinear element increases. So at point C, x increases and the operating point moves towards point B, and the operating point moves towards point B because this point unstable. That's why x increases. If a slight disturbance causes the system operating point to move point A to point D, then next case, when point move A to point D, this is the point D, this is the point D. When point A moves point A to point D on the -1 by n locus, on the -1 by n locus, then the z omega locus in this case does not enclose the critical point D. So critical point D does not enclose the z omega locus, because z omega locus, this is the z omega locus, and this is D point does not enclose. Therefore, the amplitude of the nonlinear element will decreases. That means in this point, amplitude of the nonlinear element decreases and the operating point moves further point D to the left, and operating point moves further point D to point left, this direction. That means x tends to 0 direction. Thus, point A possesses diverging characteristics. In this point, this is this direction moves point A to point B direction, and in this section outward direction. That means this is divergence characteristic, and this limit cycle is unstable limit cycle. So point A position, the limit cycle is unstable limit cycle. This is the unstable limit cycle. Next, stable limit cycle. Again, this is the -1 by n locus, and this is a z omega locus, and intersection point A and intersection point B. A operating point and B another operating point. So let the system is operating at point B. This is the operating point, which is a limit cycle. Again, intersection point, this is the intersection point. That's why limit cycle exists, and this limit cycle stable or unstable. This is our question. If a slight disturbance causes the system operating point to move from point B to point E, again, some disturbance, slight disturbance causes the system operating point, that means B operating point, move from point B to point E. This position moves point B to point E. This is the point E. Then the z omega locus in this section does not enclose the critical point, point E. This is the outside, does not enclose, that does not enclose, so x decreases, and this is the direction because x tends to 0 direction. This is the x tends to 0. The amplitude of the sinusoidal input to the nonlinear element decreases, and the operating point moves point E to point B. This is the direction. This is the direction, point E to point B. Next case, when if a slight disturbance causes the system operating point to move from point B to point F. Suppose this is the operating point, and this point moves from point B to point F. This is the point F. This is the inside of the z omega locus. This is the inside of the z omega locus. So point B to point F on the -1 by n locus. In this case, will enclose the critical point, point F. Therefore, the amplitude of the oscillation will increases, and the operating point moves from point F towards point B. This is the direction, and moves point F to point B direction. And the system operating at point B is stable because this is the converging property. In other words, the limit cycle at this point is stable. So for outside this is the stable by Nyquist sense. So x decreases, this is the decreasing direction, and when inside enclose the z omega locus, then oscillation increases. That's why x increases, and when x increases, this is the direction, and this is the stable limit cycle point, B point. So stable limit cycle point, stable limit cycle point. For the system shown in figure, this is the figure. The stable limit cycle corresponds to the point B can be experimentally observed, and this is the stable limit cycle. So this stable limit cycle experimentally observed, but the unstable limit cycle corresponding to point A, in this point, point A, unstable limit cycle cannot be observed. This is the important point. So stable limit cycle experimentally observed, but unstable limit cycle cannot be observed. Accuracy of describing function analysis. What is the accuracy? Note that the amplitude and frequency of the limit cycle indicated by the intersection of the -1 by n locus and the z omega locus and approximate values. If the -1 by n locus and the z omega locus intersects almost perpendicularly, when -1 by n locus and z omega locus intersects almost perpendicularly, then the accuracy of the describing function analysis is generally good. This is the important short question, generally good. If the higher harmonics are all attenuated, the accuracy is excellent. When the higher order harmonics are all attenuated by minimum phase or low pass phase filter, then the accuracy is excellent. Otherwise, the accuracy is good to far. If the -1/n locus and the z-omega locus intersects almost tangent, when -1/n locus, this is -1/n locus, and z-omega locus intersects almost tangent, then the accuracy of the information obtained from the describing function analysis depends on how well z-omega will attenuate the higher harmonics. In some cases, there is a sustained oscillation. In other cases, there is no such oscillation. It depends on the nature of z-omega. One can say, however, that the system is almost on the verge of exhibiting a limit cycle when the -1/n locus and z-omega locus are tangent to each other. This is the important part. Tangent to each other, then exhibiting a limit cycle when the -1/n locus and z-omega locus are tangent. What is the summary? The describing function method is an extension of the frequency response method of linear control. It can be used to approximately analyze and predict the behavior of important classes of nonlinear systems, including systems with hard nonlinearities. The describing the desirable properties it inherits from the frequency response method, such as its graphical nature and the physical sensitive approaching it can provide it, make it an important tool for practicing engineers. And next summary, applications of the describing function method to the prediction of limit cycle were detailed. Others applications such as predicting subharmonics, jump response, and response of external sinusoidal inputs can be found in the literature. Advantage of describing function. The describing functions are helps to determine the stability analysis of nonlinear systems. The location of nonlinear device may affect the stability. It is basically frequency domain technique. So we cannot get information about the time domain specification. Thank you.